Hello, everyone. I hope you're all doing well and you're staying safe. So, today we're going to continue on our series of bonus topics for ESC 190, and specifically, we're going to cover dynamic programming. So, to start off, what is dynamic programming? What better way to start a new topic with a little bit of history? So, dynamic programming was started by an American mathematician by the name of Richard Ernest Bellman. And basically, he was at a research lab uh, with the US Armed Forces. And his task was to do research in mathematics, so advanced math, and optimization. And one of the one of his main findings was this very powerful method to solve very complex optimization problems. And, as a bit of a funny story, the way he actually came up with the name dynamic programming was that he basically wanted to come up with an impressive sounding name that would still be accepted by the politicians at up top. So the word dynamic, uh, he chose that for two reasons. One being that it refers to problems that have a time varying aspect to it. And what I mean by that is, whenever we're solving the problem with dynamic programming, it's basically trying to solve one different subproblem at a time. So that's where the dynamic aspect comes from, because it's solving, the situation keeps on changing as the algorithm runs, such that at the end, when it would, put together all of the solutions, it would get a final solution. And the second reason, not as technical as the first one, is that Bellman just wanted to come up with a very cool sounding name that, you know, he he was assured that would not be rejected by the politicians up top. The second term, programming, well, that's just another name for optimization. So it has nothing to do with actually, computer programming. There are terms like linear programming, mathematical programming, and in the mathematics sense, not necessarily the computer science one, that just refers to basically tabulating a bunch of different solutions until you get the most optimal one. So to recap, dynamic basically corresponds to multiple stages in your solution that will change based on how the algorithm goes, and the programming just refers to finding an optimal solution out of several alternatives. And you're going to see very soon what that means. So the best way really, because dynamic programming is quite a broad topic, and there's a lot of math that goes into it. I mean, it was developed by a very, very famous mathematician. Um, but really the best way to understand dynamic programming is just to, get into a few examples and see where how dynamic programming can really be useful. Okay, so let's start off with the Fibonacci sequence problem. So I'm sure all of you have seen this problem before, either in ESC 180 or perhaps even in high school. Basically, the problem is to generate the nth number of the Fibonacci sequence, and the Fibonacci sequence is defined, in this recurrence relation here. So you have a couple of base cases. So f of 0, so at n equals 0 will be 0. F of 1 is just 1. And the rest of the terms are just given by the previous two. So f of 3 would be f of 2 plus f of 1. F of 5 would be f of 4 plus f of 3, and so on. So yeah, right in the definition of the Fibonacci sequence, there is a recurrence relation. So an example would be if you wanted to find the seventh element, so 1, 2, 3, 4, 5, 6, 7, the seventh element here, that would just be the result of f of 5 plus f of 6. So 3 plus 5 is 8, and so on. So there are a few different ways to go about solving the Fibonacci sequence. The easiest way that you can go about it when you're developing your algorithm is really just to read off of what this recurrence is saying. So what we can do is we can set an if statement. If n equals 0, just return the 0. And if n equals 1, we'll return 1. And else, we'll just literally write the recurrence relation as is. So we could have f of n minus 1 plus f of n minus 2, which is exactly what we see in this recurrence relation that's shown over here. Okay, so option 1 is to apply the recursive formula directly. Now let's see what would happen if we were to do that. So, whenever we solve a problem recursively, we always, if you really want to be thorough in your analysis, we usually like to draw a recursion tree. You'll probably remember the recursion trees that I drew in the last lectures on the board with quick sort, merge sort, finding the kth smallest element, and binary search. So we're going to do something similar here. We're going to trace through the code, but also draw all of the calls to our function Fibonacci underscore recursive. So the first thing, let's suppose we want to call f of 5. Okay, so we call f of 5, which means that we're going to have this node here, and when we do f of 5, well, that's not going to satisfy any of these base cases. We're going to end up having to do f of 4 plus f of 3. So, well, the first step is f of 4. So f of n minus 1, that'll be f of 4, and that'll be another call to our Fibonacci underscore recursive function. Okay, and then now if we're on f of 4, that means we need to do f of 3 plus f of 2, but we're going in a certain order here. We're first starting at f of n minus 1, so we're going to do f of 3, and after that, with f of 3, we'll have to call f of 2, and after f of 2, then we reach f of 1, which will be one of our base cases. So notice we've gone 1, 2, 3, 4, 5 calls, 5 recursive calls in a row, which corresponds to a depth of 4 in our recursive tree. But now, with f of 1, we've reached a base case, so f of 1, that just means we're going to return 1. So I'm going to denote with the green color that this node is now done, and basically we reached a base case, and that's just going to be, well, that's done for now. After that, well, we're now going to go to the next part of our f of 2 call. So we're going to reach f of n minus 2, so that's going to be 2 minus 2 is 0, which is f of 0, which will correspond to another leaf, or another node in our tree. Okay, so f of 0, well, oh man, getting way ahead of myself. So f of 0 is just another base case, so that'll evaluate to 0. And after that, that means that our f of 2 is now done. We can now return it. So that means 1 plus 0 is 1. We continue. We go back up a level to f of 3. We start off with, well, we already got f of 2, so now we move on to the next call. So we get f of 1 over here. Okay, that's just the base case, so we return it. And then now we're done with f of 3, so we return f of 2 plus f of 1, and we get 2, and so on. And you can kind of tell this is actually, you're probably getting quite bored of going through this process, but trust me, this is actually part of the point of what I'm trying to get at here. So just stay with me for now. So we have f of 3 that we just did. Now we're going to do f of 2 again. Okay, so f of 2, and how do we get f of 2? Well, okay, well, according to this line, we got to do f of 1 first. That's just the base case, so we return 1. Now we do f of 0. That's another base case right up here. We return 0. We're done with both of them, so we can add them up. Then, so we're good. We have f of 2 now. And after that, well, we got f of 3, we got f of 2. Now we're all the way up here. Now all we got to do is get f of 4. So we just add up f of 3 plus f of 2 to get 2 plus 1 is 3. Okay, well, we've been working very hard at simply a recursion for n equals, or a Fibonacci sequence for n equals 5, eh? All right, well, what's the next step? Well, okay, well, we just finished this part of the recursion. We did f of 4. Now, well, we got to do f of 3, right? Because we still need to take care of our every level of our recursion here. So we do f of 3. Similarly to what we did to the left here, we're going to get f of 2, followed by f of 1. That'll return to 1. And then we'll get f of 0 up here. That'll return to 0. And then we have both of those two. We get 1 plus 0 is 1. Now we have f of 2. Now we got to go to the right of f of 3, which is f of 1. Compute that. That's a base case. And so on. Now we have f of 3, which just evaluates to 2. And now we're finally done. We got f of 4 after a lot of work, and f of 3 after also a lot of work, but a little bit less than what we did on the left here. So that's great. After all of those calls, we ran through line by line with what had to happen here for the Fibonacci recursive version. And at the end of the day, we still got our final answer, n equals 5. Now, if you'll notice, if you count how many calls of this function we have to do, well, if you just count all the nodes, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we resulted in 15 computations in total. And I'm not going to derive this, but if you're to go over the math for, roughly in terms of n, if you had an arbitrary value of n, this would correspond to roughly 1.6 to the power of n nodes that we would need to compute in total to compute the Fibonacci sequence. And if you're interested, this 1.6 is actually the golden ratio. It's a very special number in mathematics, as you can imagine, that basically allows you to glean some more information about the Fibonacci sequence. Now, this 1.6 to the n, this basically means that the complexity of the recursive version of the Fibonacci sequence is exponential, because basically our time complexity is theta. It would run in around theta of 1.6 to the n, and you can imagine that, well, that's not really a very nice number here. It's not a very nice complexity, because the higher n gets, it's just going to get, well, in the name, exponentially larger to actually compute it. Okay, so this is clearly a drawback of the recursive approach to the Fibonacci sequence. And for the rest of this lecture, we're going to explore, using our same Fibonacci sequence example, the dynamic programming alternatives to this. Okay, so one of the approaches is to make use of something called memoization. So that I didn't mispronounce it, and I did not mistype it. It's not, I didn't mean to say memorization. I did mean to say memoization. And basically what memoization is, it is partly in the name memo, because what that actually means is that we try to tabulate a bunch of different solutions to our problem. So memoization, what we're going to do is we are going to try to keep track of a bunch of different results, a bunch of different subproblems that we solved here. So you'll notice um, in this entire tree, there are actually a lot of repeated computations that we did. So, when we did f of 5, okay, so there's no other f of 5s here, but, you'll see that we computed f of 3 to the right, and we went through the entire tree, but you'll also notice that f of 3 is over here as well. So this is what I mean by repeated computations, right? Like we did f of 3, we went through the tree, but eventually when we went back up the recursion tree, we just did the whole thing again. We computed f of 3, and then we did f of 2, and f of 0, and so on, and we just kind of wasted our time, really, because we could have just stored whatever result we got here such that we wouldn't need to go through this entire tree again. And that's basically the crux of memoization. It's that whenever we finish the computation of something that we haven't tabulated before, or we haven't kept a memo of yet, we just put that, we do the computation and we're fine with it. But whenever we come across the same sort of computation again, instead of recomputing everything by computing the tree, what we're going to do is we're going to take a look at the table where we just put, or where in the past, we already stored this result of f of 3. So, following the notes, you'll notice that f of 0 is computed 3 times. So over here, and over here. Okay, so that's already computed 3 times. F of 1 is computed 5 times. So 1, 2, 3, 4, 5. So what we're going to do is, instead of recursing down, whenever we reach a repeated problem, we're just going to look up in our table instead. And trust me when I say that looking up in a table, especially if that table could either be in an array or it could be in even a hash table. No matter what, is going to, the lookup for this operation would just happen in O of 1 time. So you can already imagine if we were to replace all of these depths by just O of 1 instead of whatever the depth of the tree is, you can already see that we're going to cut down our running time by a lot. Okay, so yeah, we're going to build up a table, and we can initialize the table with a few known values, which would basically be the base cases of f of 0 and f of 1. So let's see what I mean by that. So let's do the problem again, okay? But this time we are going to keep track of a table, and I'm just going to call it a cache, which is kind of the more, I guess, technical term for really just a table in dynamic programming terms. So let's look at the code real quick. The code it's not exactly the same as what the recursive approach was. There are some crucial differences here. Basically, I put a function, because I'm using Python, but you don't necessarily have to do it in Python, of course. The way I'm doing it is that I have a function, which I'm going to call fib compute, and basically it's just like the previous algorithm, except this recursion that I do here, where I call fib compute of n minus 1 plus fib compute of n minus 2, well, that's only going to run on the condition of this if statement. And what does this if statement do? Well, this basically checks for the problem that I'm being asked to solve, so fib compute of n. Instead of just going through the recursion immediately, I'm first going to check, have I already tabulated that in my cache right over here? So what I'm going to do is I'm going to initialize all of the unknown problems, so at the very beginning of this algorithm, to, let's say, just -1, because I'm confident that there's no way that any of the solutions to my problems will ever be negative, right? I mean, it's the Fibonacci sequence, so they're all positive or 0, like over here, but that's a base case, so it doesn't matter. I'm first going to check, is it unknown? And if it really is unknown, which is specified by -1, then I'm going to do a recursion, and I'm going to set my cache at that index, so n, to whatever the result I get for this recursion. Okay? So I start off over here where my arrow is. Cache equals, so I'm going to have 0, 1, because those are my base numbers, base cases. And then I'm just going to initialize -1 for all of the rest of the elements. So this is just a quick Pythonic way to initialize a list, like such. Okay, so I'm going to do that, and then I'm just going to return fib compute of n. So basically just going to go to this function, fib compute, going to put whatever my n value is, and I'm just going to continue to build up my cache. Now the reason I'm putting a function within a function here is just to take advantage of the fact that cache will basically be like a global variable for me. So whenever I'm modifying cache inside this function, I'm actually going to modify it no matter where I am in my fib compute recursion level, because cache is just a global variable. Okay, now let's start to build a tree using memoization. So I'm going to do the same problem with n equals 5. I'm going to start off with f of 5, and so far it seems basically like the usual recursion or the recursive approach. I do f of 5. Therefore, since the cache at 5, which is here, is -1, therefore I do need to do the recursion. I'm going to do fib compute of 4 plus fib compute of 3. Okay, so of course I'm going in sequential order, so I'm going to start off with f of 4, so nothing's new. And then because I do f of 4, that's still a -1 here, so it's not in the cache yet, which means I do need to do the recursion again. I do f of 3, that's not in the cache, it's -1. I then do f of 2, which is also not in the cache, so I call the recursion again. I then reach f of 1, okay, so f of 1, which is in the cache, so let's see what's going to happen here. Well, I'm just going to return the cache at that value. No need to call fib compute again because it's right over here, right? There's a 1. So I'm just going to return what's in my cache instead of doing another recursive call. So that's why I don't have a base case in my recursion flow here. So I get f of 1, that's done. And then, of course, since I did call it fib compute of 1, now in the next part I'm going to do fib compute of 0. So f of 0, and as you probably guessed, 0, it is indeed in my cache. So I'm going to return whatever's in my cache, which is 0. Okay, so far so good. Now, well, I completed these two calls to fib compute. Now, instead of returning like I did in my recursive approach, I'm just going to set that. I'm going to cache it. So basically store this value into my table as 1. Okay, so f of 2 is 1. I'm going to store it here. Great. Now I go back up a recursive level to f of 3. I just finished doing f of 2. Now I'm going to do f of 1. And, well, wait, there's no need for recursion here because this is just, it's already in my cache. F of 1 is 1. Just like before, this f of 1 was computed because it was in the cache, and this f of 1 is computed also because it's in the cache. So all of this is happening in theta of 1 time. Okay, so that's already done. Now I have f of 2 and f of 1. That's all complete. So now I have f of 3. I don't return it. I'm just going to put it, I'm going to update my table right here, and I'm going to put in 2. So 1 plus 1 is 2. Okay. So you can already kind of see that we are definitely not going to explore nearly as much of the tree as we did in our vanilla recursion approach. So f of 3 is done. We then, after f of 4 is done with f of 3, now we got to do f of 2. But are we going to explore any more of the tree? Well, no, because f of 2 is already in the cache. So we are going to do an early return and return cache at 2. So that just has a value of 1, and we're already done. We can immediately get f of 4, which is going to be 2 plus 1, which is 3. Great. So already making great time. We're at f of 5. We're now going to compute, after we just did f of 4, we're going to do f of 3. And well, f of 3, since we already computed it down here, it's already in the cache. So therefore, we are already done with f of 3, and we can just return that right away. Now we're done. F of 4 and f of 3 are done. So now we have cache at 5. It's just going to be 3 plus 2 is 5. And yeah, I believe I forgot to update my slides here, but this should read a 5 value. Okay, so now let's stop and think about what we just did here. You can already see visually from the tree that I drew that we definitely did a lot better than just the recursive approach. If you were to count all the nodes, we did 9 computations, so less than the 15 computations that we did before. You'll see that none of the computations that we did, so f of 4, or a better example is f of 3, we never really had to do that more than necessary because the first time we looked at f of 3, we explored the tree. And the next time we did f of 3, even though we did consider f of 3, so there's a second sort of computation with f of 3, we never expanded it and we never explored more on this node. So basically every node or every problem that we're solving is basically not solved more than 2 times. So the first time is actually recursing down on it. The second time is just checking on it and realizing that we can just get the value in the cache. So there are 5. Each of the nodes of 1, 2, 3, 4, 5, they are not solved more than twice. So that basically effectively, if we were to make a connection to game tree search that we did in the last lecture, it's kind of a way to prune our tree. So you'll remember that alpha beta pruning, that was just a way to prune our game tree when we were running the minimax algorithm. Basically, that let us not have to explore the rest of the tree. Memoization is kind of like the dynamic programming version of this. So by doing memoization, we pruned this f of 2 such that we don't need to do f of 1 and f of 0. We pruned the f of 3, where we don't need to do f of 2, f of 1, and the f of 2 wouldn't need to do f of 1 and f of 0, and so on. We pruned those aspects of the recursion version of the tree. And if you're to add up what all the time complexities of this version would be, you would find that it runs in linear time. Because, as I said, each of the problems that we did, so n equals 1, n equals 2, and so on, each of them will not run in more than twice, which means that, so maybe it'll run in O of 2n, which is basically just O of n time. And that's all because a lookup in a table runs in theta of 1 time. So it's constant time to just look up an index in a table. And remember, that can either be with an array, which is the more common approach, or a hash table. Okay? All right. So that was the approach with memoization. Now, so that was one way to do dynamic programming. There is a second way, which is to use a bottom-up approach. So both the recursive and the memoization approaches, both of them were technically top-down, right? Because, and what I mean by top-down is that, well, there was some degree of recursion in there. So both of them involved having a function, and it called itself on a smaller version of the problem. So it's top-down because we started at our n equals 5, and then we worked our way down to n equals 4, n equals 3, and then that n equals 4 would correspond to n equals 3, n equals 2, and so on. So eventually we worked our way down to our base cases of f of 1 and 0, so down, and then we worked our way back up. So we start at the top, and now we're here at the bottom. The bottom-up approach is exactly in the name, and basically what you can do here is we start at the bottom. So the bottom-up approach really is to start off at your base case and slowly work your way up to the value of n you actually care about. So even though memoization was great in that, we did top down, but we pruned the tree. It actually turns out that we don't really need to use recursion at all, if you're to think about it, because the Fibonacci sequence, I mean, how would you yourself actually compute a Fibonacci sequence? Well, what we would do, or at least what I would do, and I think most people would agree, is to just compute the f of 0, f of 1, add those up, and then just keep on adding up increasing numbers until you reach your last number in the Fibonacci sequence. And what you're doing there is basically the bottom-up approach. We started at the base case and we work our way up to the top. Okay, so the bottom-up approach, it's similar to memoization in the sense that it also uses a cache, so our table, and we're also going to initialize the base case part, so whatever I'm drawing in green here, 0 and 1. But the difference is that we are now, instead of calling Fibonacci on itself, we are now just going to iterate through directly on our table. Okay, so the bottom-up approach, it makes full use of the table in that we're going to just keep on building up incrementally our table until we reach the end of our table. And then all we're going to do is we're going to return the last element of our table. So the code for the bottom-up approach is the simplest version of the Fibonacci algorithm. Basically, we start our cache just like how I did in memoization. But now we're just going to iterate, so like a simple for loop, and we're just going to set each element of our cache to the last two elements of the cache. So cache at I is cache of I minus 1 plus cache of I minus 2, which is directly using the table and the Fibonacci formula. So what happens here? Well, we put f, let's say we have n equals 5 again. The first step is, okay, well, so let's start at f of 2 and set that equal to f of 0 plus f of 1. The last 0 plus 1 is 1. Next is f of 3. That's going to be f of 1 plus f of 2 is 2. F of 4 is f of 2 plus f of 3 is 3. And then f of 5 is f of 3 plus f of 4, which is f of 5. So basically, I'm just making use of the last two elements of the table to build it up. And wow, well, we're already done. So you can already intuitively guess that the bottom-up approach is going to end up being the fastest approach to the Fibonacci sequence. And yeah, so we only did 4 computations. And because of this, if you wanted to predict what the overall complexity is, if you were to have an arbitrary value of n, well, since we really only compute each element once, well, it's going to be just theta of n. So just like memoization, except memoization was more like theta of or O of 2n, which is still effectively theta of n. But the bottom-up approach is overall still faster than memoization here. Okay? So both of the dynamic programming approaches, memoization and bottom-up approach, both of them ended up giving you linear time. And even though memoization is a little bit worse than bottom-up approach, there's no way that it can do worse than just the recursive approach. Both of them are much, much better asymptotically because linear is way better than exponential. Okay. Now there's another way to show the in general with dynamic programming problems to analyze them, and that is to draw a graph. And specifically, I'm talking about the subproblem graph. Okay, so in dynamic programming terms, I guess applied to the Fibonacci sequence, each of these computations that we did here was a subproblem. So, well, the biggest subproblem is the problem that we're trying to solve in the first place. So that was f of 5, and f of 5 that really that corresponded to two different subproblems, which was getting the Fibonacci sequence of f of 4 and also f of 3. So f of 5 consisted of two subproblems, and f of 4 also consisted of two subproblems, so f of 3 and f of 2. Okay, so the subproblem graph, how you draw it is you first start off with your problem, or the biggest problem, which is the one you want to do, and you just draw an edge. So it's going to be a weighted graph. You draw an edge from each problem to whatever subproblem that it relies on. So you can read this off from the recurrence relation in general with dynamic programming problems. If you were to have f of n equals f of n minus 1 plus f of n minus 2, well, that means that f of 5 would have a subproblem f of 4 and f of 3. And then f of 4 would have f of 3 and f of 2, and so on. And then you just keep on drawing each of the, because the subproblem graph is going to basically have all of the subproblems that are possible, and you're going to keep on going until you reach your base cases that don't depend on any other subproblems because they are the smallest subproblems that they can be. So a subproblem graph is a visual tool to illustrate which subproblems really contribute towards each problem. And if you want to make a connection to what we've been learning with graphs, well, whenever we did memoization, that involve recursion. You're probably already guessing here that this definitely corresponds to another recursive algorithm in graphs, which is depth first search. So you remember from our lecture on graph implementations in C, you know, yeah, at least in the pseudocode, and as probably some of you are doing with the C code that you're developing, hopefully, um, we did depth first search in the recursive way. So if you were to try to solve f of 5, well, if you were to connect that to memoization, that's basically equivalent to running a depth first search on our subproblem graph. Because we start off at f of 5, we explore all of our options, and eventually we reach f of 0. We would evaluate that, and then we would just continue with the depth first search until we end up back where we started. So this would be our final finishing time if we wanted to use the same terminology as before. So basically memoization is equivalent to doing a depth first search on our subproblem graph over here. Now, another cool aspect with subproblem graphs is that we can actually make a connection to another graph algorithm called topological sort. So if you remember, that's what we went over a week ago in the graph implementation on C lecture. Um, if you're to look at the graph, well, sometimes, especially if we're doing the bottom-up approach, it helps to know which problems to solve first. And to know which subproblems to solve first, you can actually do a reversed topological sort of the graph. So just imagine all of these edges were pointing the other way. So instead of pointing towards its dependencies, the dependencies are pointing towards it. So imagine all of these edges were flipped. A topological sort on that graph would actually give you a valid ordering of computations to do in the bottom-up approach. Okay. And that's pretty much all I wanted to introduce with dynamic programming for now. It's a very, very big subject, but I just wanted to lay down the non-mathematical foundations for what dynamic programming is. And so to summarize, basically dynamic programming is useful when you have two things. So one is an optimal substructure. So that's when the solution that you are trying to compute, um, that just consists of optimal, so final solutions to subproblems. So f of 5, that consisted of the solution to f of 4 and f of 3, but f of 4 also consists of the solution to f of 3 and f of 2, and so on. So that's what I mean by optimal substructure. Um, the solution to your big problem just consists in some way, it doesn't need to be addition or via addition like the Fibonacci sequence. As we're going to see in the next lecture, it could correspond to a number of different ways to relate those optimal solutions. But as long as there's some way to relate um, your smaller subproblem solutions to your bigger ones, that's called optimal substructure. The next thing is overlapping subproblems. So basically, if you ever have a problem whereby the recurrence relation, you can see that you're solving the same problem multiple times, that's called overlapping subproblems because in the recursive approach, you would be solving the exact same problem multiple times. So if you remember from the slides all the way back with the recursive approach over here, overlapping subproblems concretely would correspond to f of 3 being computed here and f of 3 being computed over here. So the exact same problem, which you'll notice by the tree, you see you got the exact same tree that you would explore. Um, for both of them, you just solve it twice, and f of 2 here gets solved 1, 2, 3 times, and so on. So whenever we have a situation, sorry, whenever we have a situation where we need to compute the same problem multiple times, that's called overlapping subproblems. And that's always where a recursive approach tends to be very, very inefficient. Okay? Yeah. So now memoization is a method in dynamic programming that basically lets us just slightly modify our recursive approach, um, but it significantly reduces the runtime because we are keeping track of the different elements that we computed before in a table. So no longer will we have to repeatedly solve overlapping subproblems. And then the bottom-up approach, that typically performs better even because you know you no longer need to keep track of any overhead that would be due to running recursion. So calling a function from itself, that in itself does cause some overhead that can actually waste some time. Um, but that's not to say that the bottom-up approach is always going to be the best. Sometimes it's easier to visualize a memoization approach because it's more close to a top-down approach, and usually it's easier to just go off of the recurrence relation. If you were to do a bottom-up one, you would probably need to think a little bit harder about how exactly to build up from your bottom-up solution, or sorry, how to build up from your base case, which we're going to see in the next examples that we do in the next lecture. Um, and uh, another potential disadvantage of bottom-up approach to memoization is that bottom-up approach, that's basically building up a cache. And we're basically just solving every single problem until we reach um, the final the final problem, right? But sometimes you might be given a dynamic programming problem where you don't necessarily need to compute every single smaller problem. You might, it just so happens that in the Fibonacci sequence, we did have to solve to get f of 5, we do need f of 4 and f of 3. F of 4 needs f of 3, f of 2. So it just so happens that the bottom-up approach is the most suitable because we get to it is necessary to solve every single smaller subproblem, but there might be problems where you don't necessarily need to do that, and memoization might actually end up being even more efficient because we only solve the problems that we do necessarily need to solve to get the final answer. Um, and also another thing I wanted to note with the Fibonacci sequence is, maybe you guys were already thinking about that, but this actually isn't the most efficient. I mean, it is the most efficient time-wise, but it actually can be improved space-wise. And the reason that is that we actually, whenever we're at a certain, let's suppose we're computing f of 3, we really only need to know f of 1 and f of 2. And if we're at f of 4, we only need to know f of 1 and f of 2. So we actually don't even need to store, the entire table. What we could do is just store 2 elements in a table, and we'll just keep on updating those elements as we iterate through our table. Okay? So it's like when we have f of 2, we can keep track of f of 1 and f of 0. When we're doing f of 3, we can replace that 0 with whatever f of 1 had, and then update the next one with f of 2. So basically, just imagine keeping track of only 2 of them, 2 of the last elements at a time, as you're trying to compute your next element up here. Okay? So you'll find a lot that in bottom-up approaches that you might start off with a big table, and eventually you'll try to cut down space-wise by just realizing which previous elements in your table you're actually going to need. Yeah, so that'll become a little bit more apparent in the next lecture. Um, Another thing, just to end off the lecture, is to actually show the code in action. So here you can see the different uh, programs that I made. So Fibonacci recursive, Fibonacci memoized, and Fibonacci bottom up. This is the exact same code that's in your lecture slides, but I just wanted to run it in front of you guys. So I'm going to go on my terminal. By the way, if you watch the SSHFS tutorial video, I'm basically using this to have access to the ECF machines. So I just mounted my ECF onto my computer, and now I have all of my files, and I'm opening it in my Windows environment. And this is just a terminal, so I'm already in the ECF. This was dp_1.py. So what I'm going to do is I'm just going to call each of these three functions. I'm going to call Fibonacci recursive, memoized, and bottom up. And I'm going to use this time module that you can import. So if you import time, that's just going to allow me to keep track of how long it takes each of these functions to run. So I'm going to start off at n equals 30. Let's see how long each of these three take. So let's run it. Python dp_1.py. So I'm going to hit enter. Okay, so that's the answer for n equals 30. And you'll notice that my first approach, so this was the Fibonacci recursive approach. It took 0.895 seconds. The memoization approach took way less, as you can see. It only took 0.000049 seconds. And even better, the bottom-up approach took around half of that time, which remember that makes sense because the bottom-up approach was like O of n or theta of n, and the memoization was like theta of 2n. So you can already see here that it's starting to make sense why the bottom-up is the best in terms of Fibonacci. And just for fun, if you want, I can also increase this just to see how long it'll take if I just increase it by a little bit, so only by 10. If I run that, well, oh man, see, right now it's trying to compute the recursive version, and it's still running. So even at n equals 30, it was 0.895 seconds. I only increased it by 10, and look at the drastic difference in time that it's taking. And that's all because the recursive version is exponential. I could be here all day. I actually don't even know how long this is going to take. But yeah, so that's pretty much what I wanted to show you guys. Feel free to run this yourself to really appreciate why a recursive approach in some cases will not be the best way to go. And I will see you guys in the next lecture, where we will go into different, more interesting problems that can be solved with dynamic programming. Okay? Thank you very much.